What's going on? My name is Andrew Cole.
My name is David Sun. This is the Lab 9 presentation report, Hardness. The main objective of this lab is to explore the concept of material hardness, and through hands-on experience with Rockwell and Brinell hardness tests, we will discover how the material's resistance to indentation and deformation. Additionally, we will be performing quenching technique uh, to strengthen the materials and test how the materials property, how it changed the materials property. Okay. Uh, for the heat treatment, we need to wear some safety clothes such as apron, gloves, and face shield. Uh, we heat the 1018 steel until it turns orange, and we perform three different quenching technique: air, water, and oil quench. And we cool the materials down and sand it, and it's ready for the hardness test. For Rockwell, uh, for Rockwell hardness test, we perform the calibration for the C and the B scale and make sure those values are close to the label on the specimen. And second, and then for uh for each Rockwell test, we perform three trials in three different locations to get a more accurate value. Uh, and for the B scale, we test 1018 untreated aluminum, 1018 steel air quench, 1018 water quench, 1018 oil quench, and use the ball indenter with a weight of and use the weight of 980 kilograms. And for the C scale, we test 1045 still untreated and 1018 water quench, 1018 oil quench, using the diamond indenter with a weight of 1471 kilograms. And for the Brinell hardness test, we measure the diameter of the indentation three times to get a more accurate value, and with a weight of 500 kilograms, and we calculate the BHN hardness number and compare it to the actual value.
So for our data collection, right here we have the table for all of our Rockwell hardness values. So we have the scale used, either the Rockwell B or the Rockwell C scale, the unit, which would be also Rockwell B and Rockwell C. And then we have our data from 3 trials along with the average. Using this data from trial 1, trial 2, and trial 3, we're able to calculate a standard deviation for each of our tested samples. Here we have the data collection table for our Brinell hardness test. So this was only done on one sample of aluminum, as David was just saying. So using an equation, we were able to calculate the Brinell hardness number for each of the diameters found in each of our trials. Using that number, we were able to compare it to the actual Brinell hardness number for the sample tested. And for our results and analysis. So from the Rockwell B scale, it appeared that the water quenched 1018 steel had the highest RHB number. And for the Rockwell C scale, our oil quenched 1018 steel had the 1018 steel had the highest RHC number. It should be noted here that for the oil quench and the water quench samples, there were both Rockwell B and Rockwell C samples. And we have a very, very high number for our 1018 water quenched for our Rockwell B scale, which indicates that it might be better suited for a C scale to get more accurate results. And for our Brinell hardness number, using this equation over here, equation 1, where P is the force, D is the indenter diameter, and the lowercase d is the indentation diameter, we were able to calculate the Brinell hardness number for each of our trials. So from this, we got values of 86.06 and two values of 91.24. Comparing that to the actual Brinell hardness number of 93 for an aluminum alloy, we were able to yield a percent error of 7.46, 2 at 1.89, and that gave us an average percent error of 3.75%.
For the Rockwell Hardness B scale, the highest hardness was 1018 water quench, average of 197 HRB, and the lowest is aluminum, average of 61 HRB. And for the C scale for Rockwell Hardness result, the highest is was 1018 uh 1018 steel oil quench, the average of 104.7 HRC, and the lowest is 1045 still untreated with the average of 15.2 HRC. And for the Brinell hardness value, we yield a percent error of 3.75. And so, so therefore the BHN equation is reliable to calculate the Brinell hardness value.
And to conclude, for our hardness testing, we were able to see the effects of different heat treatments on a 1018 steel specimen and see how they would react under different loads and different hardness tests. We also found the differences between the Rockwell B scale and the Rockwell C scale. It was very apparent in comparing our values we got for our 1018 with the different heat treatments, comparing them on the Rockwell B and the Rockwell C scale. And then for Brinell testing, we learned how to use a Brinell testing machine, but we were also able to yield good data, finding an average percent error of 3.75%.
For the future work, we would like to experiment with more quenching with using other materials, not just 118 not just 1018 steel, and compare and analyze the Rockwell hardness value to prove that the Rockwell hardness values test is reliable.
And these are our sources, and thank you.
Think how do we do?